Hi everyone. Today we will be talking about diffusion and osmosis. In general, transport across the cell membrane. It occurs through three different mechanisms: diffusion, active transport, and vesicular transport. Firstly, we have diffusion. In diffusion, there are 4 points to be discussed. Firstly, it occurs with a long or down gradient. For example, the concentration gradient for salts, pressure gradient for gases, and electrical gradient for ions. Note, if ions diffuse along both concentration and electrical gradients, it is called electrochemical gradient. Secondly, as diffusion occurs down gradient, it is like a kid going down a slide. It does not need energy, so no ATP is needed. It is a passive process. Note, diffusion is the only type of transport which is passive. Thirdly, the factors affecting diffusion rate. There are 7 factors that affect diffusion rate. Diffusion rate is directly proportionate to 4 of them. A, the concentration gradient. B, the temperature. C, the area of diffusion. And D, its solubility in water. However, diffusion rate is inversely proportionate to 3. First, we have the square root of molecular weight. Here's why. This is because the size of molecules increases in proportion to their radius squared. The inverse of the power 2 is square root. Second, the length or distance of diffusion, or simply the membrane thickness. And third, the viscosity of fluid through which molecules of gas or salt diffuse. Fourthly, the types of diffusion. There are 3 types of diffusion: simple diffusion, carrier-mediated or facilitated diffusion, and thirdly, osmosis. Simple diffusion. Cell membrane is formed of lipid bilayer in which protein channels filled with water are inserted. Therefore, there are 3 possibilities for simple diffusion. Number 1, to diffuse through the lipid bilayer of the membrane. Number 2, to diffuse through the protein channels. Or thirdly, to diffuse through both lipid bilayer and protein channels.
Bravo.
Firstly, the diffusion through the lipid bilayer of the membrane. This occurs for lipid-soluble substances. Diffusion rate is directly proportional to their lipid solubility. The best example is oxygen. Oxygen is highly soluble in lipid, so oxygen diffuses across the cell membrane as if the cell membrane does not exist. Secondly, simple diffusion across the protein channels. Lipid-insoluble substances are unable to diffuse through the lipid bilayer. They can diffuse through the protein channels which are filled with water, provided they have small molecular weight and they are water soluble. So, diffusion across the protein channels occurs for lipid insoluble, water soluble, and small molecular weight substances. As the area of protein channels is 1/100 the area of lipid bilayer, this type of diffusion is much slower. The best examples are ions. Diffusion rates of ions through protein channels depends both on ions and channels, which are, firstly, selected permeability to ions, which depends on the size of ions, the shape of ions, and the charges of ions. And secondly, the type of protein channels. There are 2 types: non-gated channels and gated channels, which are of 2 types. Firstly, voltage-gated channels. Here gates open by electrical changes. And secondly, ligand-gated channels. Here gates open by union of a ligand with receptors at protein channels. Ligand is a chemical substance. Gates may be external or internal. Thirdly, diffusion through both the lipid bilayer and protein channels. This occurs for both water and water-soluble substances which have two characters. Firstly, a small molecular weight which allows them to diffuse through the protein channels. And secondly, they are uncharged. This is to avoid repulsion by the charges of lipid bilayer, which will reduce their velocity. Despite the fact that they are lipid insoluble, they diffuse through the lipid bilayer as bullets, depending on their very high velocity. Some examples are carbon dioxide and urea. The second type of diffusion is the carrier-mediated or facilitated diffusion. Glucose is essential for cell survival, yet it can't diffuse through the lipid bilayer because it is a lipid insoluble, or via protein channels because of its high molecular weight of 180. So, diffusion of glucose is facilitated by carrier proteins. This is why this type of diffusion is called facilitated or carrier-mediated diffusion. Here's the mechanism. Glucose molecules unite with receptors of carrier proteins by the aid of enzymes. This leads to widening of the narrow inner part of protein channels, which allows glucose molecules to cross the channels and in turn the cell membrane. Differences between facilitated and simple diffusion are related to the presence of enzymes and receptors of carrier protein. Firstly, the presence of enzymes makes facilitated diffusion 10 times more sensitive to temperature changes than simple diffusion. And secondly, the presence of a limited number of specific receptors or carrier protein leads to three things. Firstly, structural specificity, which means that only a limited number of substances that have specific structures can unite with the receptors. Secondly, competition between these similar substances for the limited number of receptors. And thirdly, saturation. This occurs when all receptor sites are engaged, which means facilitated diffusion reaches a maximum, unlike simple diffusion. Osmosis. There are 7 points to be discussed concerning osmosis. First, the definition. Osmosis is a simple diffusion of solvent, which is water, not salts. So it occurs from the site of more solvents, as it contains less salts to the sites of less solvents, which contains more salts or solutes. Secondly, osmotic pressure. Osmotic pressure is the pressure needed to stop osmosis. Because it equals osmotic force, it is used to measure osmosis. It is measured in millimeter mercury. Thirdly, osmotic pressure depends on the number, not size, of molecules. Here's why. Kinetic energy equals 1/2 mass V squared. It is the same for small-sized molecules as large-sized molecules, because molecules of small mass have higher velocity and vice versa. Fourthly, mole is the molecular weight of a substance in grams. For easy memorization, mole is the first 3 letters in the word molecular. Notice moles of all unionized substances have the same number of molecules, Avogadro's number. As osmotic pressure depends on the number of molecules. Therefore, all moles of unionizable substances have the same osmotic pressure because they have the same number of molecules. Millimole is the molecular weight of a substance in milligrams. Fifthly, osmole is the osmotic force caused by a mole of unionizable substances. All moles of unionizable substances contain the same number of molecules, so they will have the same osmotic force. However, ionizable substances, when dissolved in water, give more particles. For example, a sodium chloride molecule gives 2 ions. So, 1 mole of sodium chloride gives 2 osmoles. So, osmole of sodium chloride equals mole of sodium chloride divided by 2. 1 molecule of calcium chloride gives 3 ions. So, 1 mole of calcium chloride gives 3 osmoles. So, osmole of calcium chloride equals a mole of calcium chloride divided by 3. So, in conclusion, osmole of ionizable substance equals mole divided by number of ions per molecule. Sixthly, osmolar and osmolar concentration. Osmolar concentration is the number of osmoles or milliosmoles per liter of water. For easy memorization, the R in osmolar fits in with the R in liter. Osmolar concentration is the number of osmoles or milliosmoles per kilo of water. Note: in practice we use osmolar concentration. This is because measuring a liter of water is much more easy than measuring a kilogram of water. However, because kilogram weight is not affected by external temperature like a liter is, osmolar concentration is more accurate. However, with it being more difficult, it is not used in practice. And finally, the final point to be discussed in osmosis. Osmotic pressure equals osmolar concentration in milliosmol times 19.3 millimeter mercury. Here's why. Osmotic force, which is caused by 1 milliosmol in 1 liter of water, needs 19.3 millimeter mercury pressure to stop this osmotic force. Note: 1 liter of blood plasma contains 290 milliosmoles of different substances, for example, glucose, sodium chloride, potassium, calcium chloride, and more. To stop this osmotic force, we need osmotic pressure, which equals 290 times 19.3, which equals around 5,000 millimeter mercury, which equals around 7 atmospheric pressure. How to calculate osmolar concentration and osmotic pressure? It consists of 4 steps. Here's the first step. We calculate the amount of substance in 1 liter, as osmolar concentration is only measured per liter. For example, 90 grams of glucose in 250 milliliters of water. 90 times 1000 over 250 equals 90 times 4, which equals 360 grams glucose per liter. Step 2. To get the number of moles or millimoles per liter, divide the amount of glucose per liter by the molecular weight of glucose, as each molecular weight represents a mole. For example, the molecular weight of glucose is 180. So, 360 grams of glucose equals 360 over 180, which is 2 moles per liter. Step 3. In the case of ionizable substances such as sodium chloride or calcium chloride, 1 mole of sodium chloride gives 2 osmoles, and 1 mole of calcium chloride gives 3 osmoles. So, multiply the number of moles in 1 liter by the number of ions per molecule. So, if we put the 3 steps in one equation, we end up with osmolar concentration equals the amount of substance per liter divided by the molecular weight multiplied by the number of ions per molecule. A fourth step is needed to know the osmotic pressure. Note, mole equals 1000 millimoles, as gram equals 1000 milligrams. 1 millimole gives osmotic pressure force of 19.3 millimeter mercury. So, multiply osmolar concentration in millimoles, not mole, by 19.3 millimeter mercury. Clinical application. As all cell membranes and capillary membranes are freely permeable to water, so the osmolarity of all fluid compartments of the body are almost the same, which means the osmolarity of plasma equals the osmolarity of interstitial fluid between body cells, which equals the osmolarity of intercellular fluid, which equals 290 milliosmoles, which equals 5000 millimeter mercury, which equals 7 atmospheric pressure. Remember, diffusion occurs along gradient. It is a passive process. In simple diffusion, substances may pass through the lipid bilayer, protein channels, or both. Carrier-mediated diffusion occurs for lipid-insoluble, water-solubles, and high molecular weight substances. It does not need ATP. It is more sensitive to temperature than simple diffusion, and it is characterized by structural specificity, competition, and saturation. Osmosis is a simple diffusion of solvents, for example, water. Osmotic pressure depends on the number of molecules. A mole is the molecular weight expressed in grams. Osmol equals mole divided by the number of ions per molecule. The osmolar concentration equals the number of osmoles per liter. Osmotic pressure equals the number of milliosmoles per liter times 19.3 millimeter mercury. And finally, the osmolarity of plasma equals the osmolarity of ISF, which equals the osmolarity of ICF, which equals 290 milliosmoles, which equals 5000 millimeter mercury, which equals 7 atmospheric pressure. Thank you for watching. Don't forget to like and subscribe, and have a great day.